specifically one type of functional group, ethers. So first, what is a functional group? So those are simply an atom or a group of atoms that has distinct properties independent from the environment. So breaking that down, having distinct properties means that any compound with one of these functional groups have specific properties that are unique to that functional group. And independent from the environment means that it doesn't matter what compound it's in, having this bullet point right here, compounds with the same functional group will share the same properties, even though those compounds may look wildly different. They all have some variation of those unique properties. And also, as a side note, many organic molecules have more than one functional group, so that contributes to the wide range of variety present in the properties of organic molecules. So let's look at the structure of ethers. So it simply consists of an oxygen molecule single bonded to two R groups. And these two R groups simply represent the two hydrocarbon chains on the side of the oxygen. And you can think of the R representing the rest of the molecule, R for rest. And these two R groups can either be two alkyl or two aryl groups. And both alkyl and aryl groups are just alkanes, and alkanes meaning single bonded hydrocarbon chains. Those alkanes missing a hydrogen. So it's simply the same thing, but it's missing a hydrogen because it's bonded to an oxygen. So that extra hydrogen is replaced with the oxygen in the ether group. And the difference between alkyl and aryl groups is that alkyl are either straight or branched alkanes, missing a hydrogen, and aryl groups are a hydrocarbon ring, like a ring structure, think of benzene, that is missing a hydrogen. And so in this specific image, you can see that both of the R groups are the same, which is shown by them having the same letter with no additional markings. But if you want to show that the two R groups are different, you would have one as an R group and one as an R prime group. And as you can see here, R prime is denoted with an apostrophe right there. And finally, let's address the lone pairs on the oxygen. So those lone pairs lend themselves to other properties I'll discuss later. But one effect that the lone pairs have is making the alpha hydrogens more acidic. So how does this happen? So if you think of lone pairs, that increases the electronegativity of the oxygen here. It wants to pull electrons to itself. And so the very high electronegativity of the oxygen would want to pull the electron density of nearby molecules towards itself. And that also applies to the hydrogens that are bonded to the carbons right here. So you can think of this as a COC bond. So the hydrogen off one of those CO bonds has some of its electron density being kind of squirreled away by this oxygen that's very electronegative. So that means that these alpha hydrogens, alpha just meaning that it's bonded to a carbon that's directly bonded to the functional group, these alpha hydrogens are more acidic, which means that it has less of electron density than you would see in a normal hydrocarbon. And the COC bond right here, the C being a carbon on one of these R groups, that has a bond angle of about 110 to 112 degrees. It depends on which source you look at. And the distance between the carbon and the oxygen right here is about 140 pm. So let's go into naming. So if you've taken chem before, then you can most likely name this organic compound pretty easily. So the informal name, you would just call this ethyl methyl ether. So here you see your methyl group, here is your ethyl group, it has two carbons, that's how you know it's an ethyl group, and here is your ether. Pretty simple, right? But if you look into the official naming, it might get a little bit harder, and that's because official naming is very thorough, and it's especially useful when you have more than one functional group, because it's easier to discern which functional groups are in there versus naming it informally. So the general form of ethers for IUPAC naming is going to be alkoxyalkane. And so let's break that down. So first, you need to look at the longest carbon chain, your parent chain. So you're looking for your longest alkane. And that's going to be, in this case, your ethane right here. So there's 2 carbons, which is longer than 1 carbon, and thus this is your parent chain, and that's going to be your alkane in this general form right here. And so you would treat the other chain plus the oxygen as a substituent group. So this is your alkyl group right here, and here's your oxygen right here. Alkyl plus oxy is alkoxy. That's going to be your substituent group. And that's how you get alkoxy right here, alkyl, oxygen, and alkane, which is your alkane right here. And of course, you can add numbers to denote the location of the oxygen or any double bonds, triple bonds that might be in your compound, but this simple molecule doesn't need it right here. Okay, so let's get into an example after I've explained the general form. So first, we're going to look for the longest carbon chain, your alkane. This is your longest one because 2 is bigger than 1. And so your second word is going to be ethane. And so that leaves treating this as a substituent group. This is a methyl group, this is an oxy. Methyl plus oxy is methoxy, thus you end up with methoxyethane. So that's pretty simple, right? And then let's finally go into properties for the general explanation. So you can see the properties from the structure of this compound. And again, this is just ethyl, methyl, ether a second time because it's pretty easy to explain. So first, let's explain how it has a low melting point. So having a low melting point corresponds to having low intermolecular forces, a low relative strength of those intermolecular forces. And as you know, hydrogen bonds are very, very strong intermolecular forces. So when you lack those strong intermolecular forces, your IMFs are relatively pretty weak. So as you can see here, there are no hydrogen bonds here because none of the hydrogens are bonded to FON, fluorine, oxygen, nitrogen. The oxygen here is just single bonded to carbons, so it has a pretty low IMFs, and that results in having a low melting point / boiling point because it's very easy to separate these molecules from each other with relatively low energy, which here you can see the method of vaporization. These liquid molecules are separated from each other and can escape as high energy gas molecules. So if you think of an ether which has relatively weak bonds connecting them to each other, then it takes less energy, which corresponds with a smaller boiling point, to make them evaporate. And we call this volatile. And volatile just means that the liquid state of your compound, if you apply relatively small amount of energy, low temperature to it, then it'll evaporate very easily. And also, ethers are nonpolar as well. You can see this from the presence of 2 alkyl groups right here, right next to the oxygen. And the relative electronegativities of the carbons and hydrogens in those alkyl groups are pretty much the same. So these are relatively nonpolar amongst the functional groups. And if you remember, the oxygen has 2 lone pairs, and that's depicted in the slide right here. You see there's 1 lone pair, 2 lone pair on that oxygen. And that means that the oxygen, those 2 lone pairs, can be used to make hydrogen bonds with other molecules that aren't ethers. So just to clarify that again, there is no hydrogen bonding between ethers themselves, but ethers can form hydrogen bonds with other molecules without that ether functional group. So that means that it's a relatively good solvent for nonpolar organic molecules. Nonpolar because ether itself is nonpolar, like dissolves like, and solvent because it can dissolve those compounds pretty easily. It starts from here if you imagine the red molecule of the ethers and this one as your nonpolar organic compound, the ethers form pretty strong bonds with these nonpolar organic compounds, and it just disperses it evenly within the solution and it dissolves it. And going back to it having no hydrogen bonds and it being relatively nonpolar, it thus has a relatively low reactivity amongst the functional groups. So we can compare adding a functional group as adding a spice to food. So if you think about adding flavor to food, many foods, like if you add pepper to chicken, you add pepper to fish, you add pepper to your spinach, they all have the same predominating flavor of pepper, even though those dishes themselves are very different from each other. And so that's analogous to how having the same functional group results in maybe very different organic molecules having similar properties because of those same functional groups. But like how your pepper spinach and your pepper chicken, they may taste similar, but they aren't exactly the same flavor. That's also like how organic molecules with the same functional group have similar properties, but they do differ slightly. And finally, if you add a predominant flavor to your dish, then that would change the recipe's name, right? So if you think of this fried chicken, you add a bunch of pepper, it becomes pepper fried chicken. So that's kind of like how adding a functional group to an organic molecule would change the name of that organic molecule. And finally, let's end with some applications of ethers. So this stems directly from the properties of ethers. So if you remember, we said that ethers are very volatile, which means that it evaporates quite easily. So let's consider perfumes. So perfumes are going to be liquids that you keep in like bottles, spray bottles, what have you. And you ideally want it to evaporate pretty easily so you can smell the vapors of the perfume, right? So that means that the qualities you want in your perfume is that it's liquid at room temperature, but when you apply very little heat to it, like if you apply it to human skin, that heat from the human skin will cause your perfume to evaporate. And that's essentially volatility. And if you think about ethers, most of them are liquid at room temperature, and when they're applied with low temperatures, like maybe the temperature of human skin, they do evaporate pretty easily. And those vapors can travel to the scent receptors in your nose and you can smell it. So that's why ethers are used pretty widely in perfumes. In the same vein, ethers are also used as an anesthetic because for certain anesthetics, you do inhale them and then you either get numbed or you get like knocked out. So back in the day, ethers were used as anesthetics because you can inhale them pretty easily. Those vapors would come from relatively low temperatures. But ethers are not used in anesthetics today, at least in richer countries. Some countries do have to resort to ethers. They're not exactly very safe because ethers are quite flammable and you don't want them near your patient. So that's why ethers aren't widely used as anesthetics today. And finally, they're also used as solvents in the extraction of nonpolar organic compounds. So if you think about the properties that we discussed earlier, how it was good for nonpolar compounds because it's also nonpolar itself, and it's a good solvent because it can form hydrogen bonds with the lone pairs on this oxygen right here. It can be used in this extraction process. So we don't have to exactly break this down step by step, but essentially you would combine your ether solution with a solution containing your wanted nonpolar organic compound, and those ethers would dissolve those organic compounds. And since ethers are relatively not very dense, they rise to the surface because dense stuff goes to the bottom, light stuff goes to the surface. You can see that in many things like oil and water. then that means that you can separate your wanted organic molecule pretty easily